Okay, it seems to me that most of the complexity involved in learning the Mitchell-Benabau language is centered around the symbol for all. Because, I mean, yes, Mitchell-Benabau language does support exponentiation, but the main way it's used is in the context of universal quantifiers, as in for all, and existential quantifiers. However, existential quantifiers are defined in terms of for all. And so understanding how for all works, what that symbol means, how it works in formula and so on, seems central. And there's a particular result which basically allows us to do substitutions and substitute for all into expressions, which kind of sweeps a lot of this complexity under the rug. But we want to understand the reasoning behind this kind of rule. So let's go. Suppose we have a formula that is a type omega term, gamma, and it has a free variable, just one free variable, b. And we have another formula, phi, and that has free variables b and a. Now, this is the main formula that we want to prove, this innocent looking expression that saying that gamma implies phi is equivalent to saying that gamma implies for all a dash phi. Okay? So in other words, what we're saying is that gamma implies phi if and only if gamma implies for all a dash phi. So we want to understand this, but we're going to go quite gradually and take a kind of tourist sort of attitude toward this, because we really want to understand the different phenomena we're going to see in this proof. So firstly, what does phi implies gamma mean? Well, what it's saying is that if we do, what does gamma imply phi mean? Well, what it means is that if we do the extension of gamma over the b's and a's, we get a sub-object which is contained in the extension of phi extended over b's and a's. Now, there's already a bit of a curiosity here, because I mean there's no problem thinking about this, the extension of phi over these b's and a's, because phi is a term which depends on both b's and a's, but gamma here only depends on b's. So when we extend it over a's as well, we're going to get a larger kind of sub-object which kind of has all the a's filled in. It's going to be a sub-object of b times a, but we're basically just going to sort of multiply all the stuff in b, which is in this sub-object, by a in some sense. Anyway, we're going to see this much more clearly, so don't worry about understanding it at the moment. But the next thing we want to understand is, what's this other expression mean? That gamma implies for all a dash of a phi. Well, the thing is here that phi had two free variables. It had a free variable b, it had a free variable in capital B and a free variable in capital A. But when we do this for all thing, we're really bounding the variable in A. So now we're really talking about doing extensions just over the b's. And that suits the gamma fine, because the gamma is naturally defined in terms of b's. It only has a free variable in b. So anyway, this is equivalent to writing that the extension of gamma over the b's is contained in the extension of for all a dash phi over the b's. Well, all right then. So let's start to understand what this stuff means. We'll start with the simpler one, which is this one here. And we're going to focus on the gammas for a start, because they don't have any sort of exponentiation involved in them. So we have this extension of of gamma over the b's. And this is going to be a sub-object of b, and we're going to call it S. Now, what is it? Well, it is the sub-object classified by the interpretation of gamma over b's, okay, which we just call gamma. And we could also call this the classifying arrow of S, since S is the sub-object classified by this thing, okay? Whoa. We could also call this the sub-object classified by S, because S is the sub-object. Excuse me, I'm getting tongue twisted. Okay, so we have this extension, which we call S, and we can think of this extension as the sub-object classified by this gamma here. Or equivalently, we could say that gamma is the classifying arrow of S. That's the phrase I was looking for. So, I mean, basically, we're just saying that we have our sub-object classifier here. Here's the true arrow. Here's gamma. If we pull back true along gamma equals chi of S, we get S here. Which is this extension up here, okay? Right. Now then, the next thing we want to understand is what this is, okay? So we understand now what it means to do the extension of gamma over b's, but up here we have the extension of gamma over b's and a's. So what's that mean? Well, it turns out it's going to be equal to this, but we'll prove this. But anyway, first we want to actually prove that this is a legitimate object. So I claim that if we take this S defined here, and we times it by the identity of A, we get a monic, okay? So this is going to be a monic. It's going to be a sub-object of B times A. It's going to be a monic from zeta times A to B times A, S times 1A. Okay, so how do we know that this is monic? Well, actually, I'm not going to show that this is monic yet. I will do momentarily. But firstly, let's understand a bit more about what this is. So what's it mean to have the extension of gamma over B and A? Well, this is going to be the sub-object classified by the interpretation of gamma over B and A. Now, gamma just depends on B, so when we do this interpretation, we want to put a first projection in here, because this is a term which just has a free variable B, but we're interpreting it over B and A, so we want to do the first projection to grab the B. Okay, so in other words, the interpretation of gamma over B and A is gamma after the first projection. Right, now, let's do what I said. I wanted to show that S times 1A is monic. Well, what is it? It's S P1, P2. So let's show this. So we'll do this usual kind of proof. Here's S times 1A. We'll show that we'll assume there's two arrows into it from some general object H. We'll call those arrows B1, A1 and B2, A2. And we want to show that if S times 1A of B2, A2 equals S times 1A of B1, A1, then B2, A2 equals B1, A1. So let's go. So here we've got our inputs, and we'll assume now that S times 1A of B1 comma A1 is S times 1A of B2 comma A2. Well, since we know what S times 1A is, we can just work what this out is, and we'll have that the second component on each side is just going to be, well, it's going to be A1 on the left and A2 on the right. So we have A1 equals A2. And then thinking about what happens on the left, I mean, we'll get S of P1 of B2 comma A2. That's S of B2 on the right. Similarly, we'll get S of B1 on the left. So we have S of B1 equals S of B2. But we know that S is monic. So we're going to have B1 equals B2. So we know that A1 equals A2 and B1 equals B2. So we have that B1 comma A1 equals B2 comma A2. And we're done. We've shown that this is monic. Obviously, a similar argument could show that, you know, the product of monics is monic in general. But anyway, let's carry on. This is like our main sort of claim for the moment, is we really want to show that this extension of gamma over the B's and A's is just identical to S times 1A. All right then, so let's do this. So suppose we have an arrow from a general object to M to B times A, and we'll call it B double dash comma A double dash. Now, in order to show that these two things are equal, we just want to show that B double dash comma A double dash is going to be in this extension here, if and only if it's in S times 1A. So let's go. B double dash comma A double dash is in this extension here, extension of gamma over B's and A's, if and only if doing the interpretation of gamma over the B's and A's, operating on B double dash comma A double dash is TM. This means true after the unique arrow from M to the terminal object. And that's true. We'll just sort of interpret this. So that's true if and only if gamma of P1 of B double dash comma A double dash is true. That happens if and only if, well, true M, but I'll just call it true just for short. And that happens if and only if gamma of B double dash is true. And that happens if and only if the interpretation of gamma over B of B double dash is true. And that happens if and only if B double dash is in the extension of gamma just over the B's. And we know that that's equal to S. That's what we defined S to be. And that's true if and only if there exists a K such that B double dash is in S. Sorry, if and only if there exists a K1 such that B double dash is in SK1. That's just a definition of what in means. And that's true if and only if there exists K1 comma K2 such that B double dash comma A double dash is in SP1 comma P2 of K1 comma K2. So what's this mean? Well, oops, well, what's being equal there? Well, basically, I'm adding some sort of redundancy here because we can all, you know, if we can find K1 such that B double dash is equal to SK1, then we can use that same K1 here to get this first component, these first components matching up, because on the right we're going to have an SK1 and as a first component, and on the left we're going to have a B double dash as a first component. And then if we can't find a K1 to make this work, then we can't satisfy this equation on the first component. But the second component of this equation doesn't really matter because, well, I mean, it's automatically satisfied, because if we just set K2 is equal to A double dash, we can always satisfy the second component. So since the second component of this equation's always satisfied, we have that this equation can be satisfied if and only if it can be satisfied in the first component, which happens if and only if this last statement holds. Anyway, we can simplify this to say that this happens if and only if B double dash comma A double dash is in S times 1A, because S times 1A is this. Okay, and then we're done. That's it. And so this is a picture of what we have so far then. We have this extension of gamma just over the B's. This is the kind of natural way you think of what gamma means as a subobject. And it has this classifying arrow, which is the interpretation of gamma. But then we have this extension of gamma over B's and A's. And I've just showed that this is equivalent to this thing times 1A. And here's its classifying arrow down here. Okay. So there we are. Now, how are we to think of this S times 1A, or equivalently this interpretation of gamma over B and A? Well, we can think, I mean, let's think about what's happening in set, for example, because it's simpler. So we have this kind of extension of gamma over B, and that's just basically going to be a subobject of B. So if working in sets, we can just say it's a subset of B. But we've shown now that this interpretation of gamma over B and A, we just sort of get the same subset of B, but then kind of sweep it up along all the A's that it's contained in. Okay, so that's what it means to say that it's equal to this times 1A. Okay. I mean, essentially, if we take this subset and then do the Cartesian product of it with A, we get something that looks like this subset. Okay. Anyway, that's enough about the gammas. Now we want to understand the phi's. So we know that phi has three variables B and A. So when we do the interpretation, when we do the extension of phi over B's and A's, we're just going to get some subobject of B times A. I mean, we could really call it a relation on B and A if we like. That's why I'm using this letter R to denote it. And so we can just think of it as a sort of general, I mean, in set at least, we can think of it as a general kind of subset of B times A. So let's go through this and understand what this means, because this is very interesting. So let's let this extension of phi over B and A, we'll call it R, as I say, and it's going to be a monic into B times A. Now that's going to be the subobject classified by the interpretation of phi over B and A. We can call this the classifying arrow of R if we like. Now this is the interesting one.